Work. Work is the force applied over a certain displacement, a distance that has both magnitude and direction. So work, its units are going to be Newton meters or joules, because we don't want to confuse Newton meters with torque. So F times delta D, joules is the unit of work. So because force is applied over a displacement, if the net displacement is equal to 0, then no work is done. So it may seem sad if you go around a circular track, pushing an object around the track. It may feel like you've done a lot of work, but technically speaking, physics-wise, you have not done any work. If the displacement is in the f-axis direction, then F is equal to ma, like normal. And if the displacement is done in the y-axis direction, then the force is going to be equal to m times g. So here's an example. How much work is done as a 30-kilogram box is moved from 0 meters per second to 20 meters per second over 50 meters? So we're assuming here, because we're not using words like lifted or brought up or brought down, that this is work that's done in the x-axis direction. So I have my VI, my VF, my mass, and my delta D. So using those, I first need to find A. So I'll use VI, VF, delta D, needing to find A. This will be the equation that I choose. So to solve for A, I'm going to first divide both sides by 2 delta D. And now I'm first going to subtract VI squared from both sides, and then divide by 2 delta D. And so I get A is equal to VF squared minus VI squared over 2 delta D. So if I plug in my values, VF is 20, so that's 20 squared, minus VI, which is 0 squared, over 2 times, and my delta D is 50. So that ends up being 400 over 100, or 4 meters per second squared, is my acceleration. So now that we have A, we can find F. F is equal to ma, so my mass is 30, and my acceleration is 4 meters per second squared. So if I multiply those two, I get 120. And if I apply that over the 50 meters, then I will have exerted 6,000 joules worth of work. So it takes 6,000 joules worth of work to accelerate a 30-kilogram box over 50 meters, from 0 to 20 meters per second. If my distance was smaller, it would take less work. If the mass was smaller, it would take less work. If I didn't have to accelerate it to as high of a final velocity, that would also take less work. So work really is a way of looking at how hard or how much effort you have to put in. And another way of thinking about it is calories. So calories are another unit of work. We're all used to that. And when we think about calories in the food that we eat or calories that we expend, we're really thinking about the work that we end up spending. So how much work would it take to lift a 50-kilogram box to a height of 25 meters? So this is going to be in the y-axis direction because of the word lift. So again, this is one of those hidden words that gives you clues as to what's going on. So because it's in the y-axis direction, the force that I have to use is Fg, which is equal to mg. So work is equal to F times delta D, mg, and h is the height, right? So it's going to be equal to 50 times 10 times 25, or 12,500 joules. So although g is negative, because work is done to the object against this, work is positive. So in this case, we're taking the absolute value of g. There's also work to overcome friction, otherwise known as WF. So WF will be the friction force, which makes sense, times delta D. And remember that friction force always opposes the direction of motion and makes it harder to use. So work lost due to work to friction is often called lost work because it takes away from the actual work done to move an object. So if I wanted to go back to that first example, and I wanted to move this box and accelerate it from 0 to 20 meters per second, 30-kilogram box, the amount of work that I have to put into it, this 6,000 joules, is my net work that I have to put into it. If I have work lost due to friction, then I will have to put in more work above and beyond that to overcome the friction that is there, which makes sense, right? Because really what's happening is that my F net is going down. So in order to make sure that my pushing force is enough to compensate for that, I'll end up having to do more work. And oftentimes people take advantage of that, right? So think about a sports team. One of the classic things that they have you do is to drag this really heavy object across a rough surface. What they're really trying to do is to get you to do more work to build up your muscle mass, to build up your endurance. And the more work you have to do has to do with not just the large mass that you're trying to accelerate, but oftentimes you're accelerating it in such a way that you have a lot of friction force acting against it. So the amount of work that you have to put into it, above and beyond it, is going to be a lot more because you have work lost due to friction. Same thing happens when we talk about exercise bikes or something. Oftentimes they will take something and they will add resistance to it. That resistance really is just adding friction force.